Hello, welcome to Meki Teki. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support and watching my videos. Today's topic of interest is thermal conduction. We know that the thermal conduction or a heat transfer takes place according to second law of thermodynamics. Second law of thermodynamics, it says about quality of heat transfer. It says the quality of heat transfer. So this is the main theme of understanding the modes of heat transfer. Okay, what are the modes of heat transfer? We have three modes of heat transfer. One is conduction, convection and radiation. Conduction is the metal to metal heat transfer is called a conduction, and a metal to a liquid or liquid to air, the phase change, we know that we are having three phases. One is solid, liquid, gas. So if the heat transfer takes place from solid to liquid or liquid to gas, it is called as an convection. So convection means a heat transfer. The pace between the two different paces heat transfer is happen. So that is called as a convection. And radiation means without any intervening medium, without any intervening medium or a vacuum space or with the help of an air, if we feel the heat transfer takes place like that in electromagnetic waves. So this is called as an radiation. The one such great example is, we can say, boiler. Let us consider, so this is a boiler. So boiler, it is having metal, it is having liquid, it is having heat transfer through air also. So boiler is a very good example of all modes of heat transfer. Or if you are sitting in outside and if you are making a tea with the campfire, so it is a better example of the three modes of heat transfer. If the heat transfer from metal to metal, if the beaker, if the bottom of the beaker to your handle, so it is called a conduction. So it is called a conduction. And the beaker to the tea, it is called convection. And if you are feeling a heat without anything, so that is called a radiation. So these are all the three modes of heat transfer. So these three things are governed by second law of thermodynamics. In this video, we are going to see in detail about conduction. So what is meant by conduction? A metal to metal heat transfer, a solid to solid heat transfer, which is called as a conduction. So how the conduction is happen, how the heat transfer is happen? The heat transfer takes place with the difference in temperature. If I'm having my hot side in one side and cold side in other side, the heat transfer takes place from hot side to the cold side. So this is called as an conduction. With the materials, the lattice vibration of the materials, the heat transfer is being happened. So this is called as a conduction. So for this conduction, we have an parameters like the temperatures, two different temperatures, area of the metal, thermal conductivity of the material, and the distance. So With the help of these parameters, we found that is our Fourier found an equation for heat transfer. Heat transfer is directly proportional to area, and heat transfer is directly proportional to del T by L. So these are all the relation. If the heat transfers is equal, Q is equal, therefore the Q is directly proportional to A del T by L. L or X, or we can say X, the distance is X. dt by dt by dx I say. So, in order to make the proportionality constant, that is Q is directly proportional to area into dt by dx, we put a constant in order to eliminate this directly proportional. We add a material constant, that is thermal conductivity, into A into dt by dx. So this is the Fourier's law of heat conduction. Fourier's law of heat conduction. So this is the formula. This is the formula for finding the heat transfer by conduction. So this is takes place from solid to solid. This is conduction is takes place by means of solid to solid heat transfer. So with this information, I would like to start my own content. So here the heat transfer takes place according to second law of thermodynamics, since it deals with quality of heat content, or quality of heat transfer, we can say. And conduction means it is happen between solid to solid. The Fourier law addresses the conduction, that is Q is equal to Ka del T by L, dt by L. Del T is equal to the hot side minus the cold side. The hot side minus cold side. Next is the convection. Convection is it is postulated by Newton's law of cooling. It is solid to liquid is called convection. So it is governed by an equation, Q is equal to HA del T. HA del T. And radiation is governed by many. Radiation is postulated by many, and there Planck is an important one. Planck, Wiens, Stephen Boltzmann, Kirchhoff law, and Lambert cosine law. Like that, many peoples have derivated the radiation. Radiation means the electromagnetic waves. By means of an electromagnetic waves or air, it can be done. The quality of heat content is governed by an equation, Q is equal to sigma into A into delta T power 4. Here the sigma is the Stephen Boltzmann constant, where this is equal to 5.67 into 10 power minus 8. So minus 8 watt per meter square Kelvin power 4. So this is the constant about the sigma, Stephen Boltzmann constant. And also all modes of heat transfer is done in boiler, and superconductor is a pipe is a superconductor. And next we are going to discuss about the point functions and path functions in heat transfer. If I said point function, the temperature and pressure are the point functions, and the path function is heat, work and power. Here an important factor, that is called the reheat factor, is been there. Reheat factor is always greater than 1. Reheat factor is always greater than 1. So reheat factor is equal to cumulative, the ratio of cumulative heat drop to the isentropic heat drop. It is ranges from 1.02 to 1.04. So this is the range of reheat factor. So cumulative heat drop to the isentropic heat drop. And here we are going to discuss about the conduction. So the Fourier assumption should be made. The real heat transfer and Fourier assumption should be compared here. In real time, heat transfer is unsteady, it is three dimension, and it is normal to the surface, that is temperature varies and the material are heterogeneous. So this is the complex in real time heat transfer. So in order to simplify the problems and get solution, if there is a unsteady, it becomes non-linear. If there is a heterogeneous, it is also becomes non-linear. So non-linearity we cannot solve directly. Therefore we made an assumption in order to get the real time problem, in order to get solution of the real time problem. So for that, the assumptions made are it is steady instead of unsteady. We make it as a steady. Instead of three dimension, we make it as an one dimension problem. And heat transfer, the heat thermal temperature is constant. It is a boundary surface. It is a boundary surface, and the material is homogeneous material. The material is homogeneous material. So this is the Fourier assumptions. So these are all the Fourier assumptions is being made. Next, the thermal conductivity. So as I said, conduction, it is a free flow of electrons. We know that in the solid, in the solid, the molecules are, it is made compactly. It is made compactly, and all the molecules having an electrons, all are free electrons. So free flow of electrons made conduction. Free flow of electrons made a conduction. Solid and liquid medium under stationary medium, that is called convection, is happen, and molecular collision, lattice vibration of the molecules will done the conduction process. The Fourier law of heat conduction governs the conduction process. The governing equation is Q is equal to minus Ka del T by L. Here the minus sign indicates the temperature flow from higher side to lower side. Nothing there. Okay. If we can make an equation Ka del T by L. So this is nothing difference between the minus as well as the plus. The minus sign indicates heat transfer is from higher side to lower side. So uh, this is the function. That is why we are putting a minus before the K. Okay. Next, the temperature profile for different types of heat conduction. So wall without internal heat generation. Without heat generation, the temperature profile is linear. Wall with heat generation, it is been parabolic. That is, if we have a wall, if we have a wall, so this is my material. So this is my material. Here it is T2 higher side. Here it is T1 lower side, where the heat transfer, which is linear. Heat transfer is linear if there is no heat generation inside. If there is any heat generation, it is becomes parabolic. If it is a cylinder, it is a logarithmic. For a sphere, it is a hyperbolic. Unsteady state heat conduction, it is in exponential form. It is in exponential form. Now we are going to discuss about the difference between the thermodynamics and heat transfer. So thermodynamics, generally heat is made in kilojoule per kg, or heat transfer it made in kilojoule per second, that is kilowatt. So it is in here heat and mass transfer. Heat transfer, we make the quality of heat content in kilowatt, that is an useful work, where here it is a kilojoule per kg. So here In the thermodynamics, modes of heat transfer is not at all taken to account, where in the heat and mass transfer we account the modes of heat transfer, whether it is in conduction or radiation, we can take it into account, whereas in the thermodynamics we won't take care. And thermodynamics or time is invariable, whereas in heat transfer time variation is taken into consideration. And thermodynamics, we make all the conditions are equilibrium condition is made. In heat transfer, non equilibrium conditions were made. So for this condition, for this heat transfer, we make four different equations, that is Fourier-Biot heat conduction equation is the general form of an unsteady with internal heat generation. Generally, if I said Fourier-Biot heat conduction, this equation, the general form is an unsteady with internal heat generation. If I said Laplace, it is steady without internal heat generation. If I said Poisson, it is Poisson equation means steady with internal heat generation, and diffused equation is unsteady without internal heat generation. So here the Laplace and Poisson is always for steady. The Laplace and Poisson is always for steady, whereas the Fourier and Biot is always for unsteady, always unsteady. And if I said steady, the Laplace and Poisson equation can be used. If I say without internal heat generation, the Laplace and Fourier-Biot equation can be used, and opposite in two ways. And 2 and 3, the Poisson and diffusion is opposite. Is simply an opposite. The Poisson is an with internal heat generation. Diffuse equation is a without internal heat generation. That is very simple. And Poisson is for the steady, and diffused equation is for unsteady. So that is a difference between the Poisson and diffusion equation. Okay, so with this I'm going to conclude the today's session. So if you have any doubt, please let me know in the comment section, and I will put another video for clarifying your doubts. Until bye bye from Santhosh, and I would like to thank you all.